Hi, this is Sanjay Kamat, and today I'm going to share one video with you. So let's begin. Okay. So as you can see, first of all, I want to show you the procedure how to design the butt weld and the fillet weld. Okay, and then and also the simple beams or the compound beams. So this is for I section only. Okay. Because I'm showing I section only because I'm solving for I section only. So let's procedure steps number 1. We have to find first of all moment of inertia about the z-axis. After finding that, we have to find the and we have also the formula z suffix I suffix z is equal to bdq by 12 minus twice bdq by 12. And this is always in mm power 4 millimeter power 4. And then second step we have to find for I section is that we need to find the modulus of the section. That is this is represented by z suffix is equal to I suffix z by y suffix maximum. Y maximum is equal to where y maximum is equal to d by 2, and is also always in mm. After finding this, after finding modulus of section, then we need to find the moment about the plastic neutral axis. For this we have a formula m is equal to 200 into 16 into m suffix y into 816 at the top, and means this I will tell you when solving the problem, and then plus 400 into 16 into here you can see 16 into fy into 400 at the bottom also we have to find. And then after finding that, we have to find the total modulus of this section, that is denoted by z is equal to m by f suffix y, and is also, and this is always in millimeter cube. This is always in millimeter cube. After doing this, come to the next step. Okay, this is fourth step. This is in fourth step we need to do is simplify this section. Classify this section. We have to classify this section in what. So to classify this section, we have the another formula is equal to 250 by f suffix y whole power half. And where f suffix y is equal to this is nothing but 250 is equal to, this is nothing but a standard value which is given in this code book. Okay, 250 this way, this is 280, 260, in between this 250. And then after calculating this, we have to calculate the another. We have to now, after calculating these all things, we have to check now. We have to check what? We have to check shear force, and then we have to check the deflection, and then after checking the deflection, we have to check the allowable deflection also, and then we at the second last we have to check the web buckling also, and for web buckling also we have the formula, and then lastly we have to check what, then crippling also, web crippling. For this also we have a formula. So one by one I'm going to say. Okay, so to check the shear, we have a formula b suffix d is equal to fy by root 3 into 1 by gamma mo into shear area. Shear area is nothing but d into here you can see is nothing but d into t suffix w. And what is that t suffix w, d, these all things I will tell you after this. Okay, and after finding this, after checking this shear force, then after we have to check for the deflection, and for deflection is denoted by delta. And its formula is p suffix w into L power 4 by 8 E 80 I suffix Z, and where P suffix W is equal to working load by this working load by 1.5. After calculating, after checking deflection also, after checking deflection, we have to check for allowable deflection, and allowable deflection is always denoted by delta allowable. Delta suffix allowable is equal to effective length by 300. This is the formula. This is the formula to check the allowable deflection. After checking this allowable deflection, we have a in this checking also there is a condition. If that condition satisfy, then it is safe. If not, then it is not safe. Okay, delta is greater than, if delta is greater than allowable deflection, then it is safe, whether it is fail. Okay, whether it is not safe. Okay, then it is not. Then after checking that deflection, we have to check for web buckling also. Web buckling checking formula is B1 plus N1 into T suffix W into F suffix C, and where lambda is equal to 2.5 into D by T suffix W. This is the formula to check for web buckling, and lastly we have to check for the web crippling also. And for crippling, for checking the web crippling also, we have another formula, that is F suffix W is equal to B1 plus N2 into T suffix W into Fy into 1 by gamma suffix mo. Now for this also we have a now I am going to say about representation. B1 is what, N1 is what, T suffix W is what, into F suffix C is what. These all things I am going to say. Okay. Up to now I said formula only, and how to check that only. Okay, how to check deflection, shear, web buckling, and web crippling, formula only. Now I am going to say that symbols in full details. Okay, so that is here you can see M suffix D is nothing but MD is nothing but buckling resisting moment. Earlier I said MD, but I didn't said buckling resisting moment, but MD is what here? Buckling resisting moment. Now earlier what I said? Fy only, F suffix Y only, but what is here? F suffix Y is, if you see, then what is F suffix Y? F suffix Y is material design strength. Then after, earlier I said Z suffix P, but I didn't say what is Z suffix P, but Z suffix P is plastic section modulus. Okay, this is the representation and the symbols to denote the to check the deflection, web crippling, web buckling, and then now beta suffix B is equal to 1.0 for plastic and compact section. This is the representation. And then gamma mo is equal to, gamma suffix mo is equal to partial safety factor for material, and B suffix U is equal to factored shear force. Earlier what I said, B suffix U only, but now I am saying full form of that. B suffix U is factored shear force. If anybody says B suffix U is what, if you don't know, then simply B suffix U is what? B suffix U is factored shear force. If you say, then other people know, no? That's why we need to know what is that B suffix U also. And then B into T suffix P is equal to area of flange plate. B into and then D is nothing but depth of the rolled beams. D is what? D is nothing but depth of the rolled beams. And then now see, if you see, I suffix z is what? I suffix z is nothing, it is what? Moment of the inertia with respect to the z axis, yes or no? And then f suffix w, earlier what I said, f suffix w only, but what I didn't said, f suffix w is what? F suffix w is here. If you see, strength of the wave crippling. After knowing this, we need to know b suffix s also. B suffix s is nothing but width of the stiff bearing. And then come to the next point, it is n2. N2 is nothing but length acquired by the separating the flange to the wave junction at a slope of I is to 2.5. And then after knowing this, f suffix y is what? F suffix y is yield stress of the wave, and then after knowing this, we need to know gamma mo. Gamma mo is what? Gamma mo is partial safety for bearing is equal to 1.1. This we need to know from this IS code book. IS code B is here. Okay, as per here, IS 800 is to 2007 from this code book. We will know this value. And then after knowing this, okay, FCDW is what? FCDW is strength of the effective wave buckling. After knowing this, and then after knowing, then A suffix W is cross section area of the wave. N1 is what? D by 2. T suffix W is thickness of the wave. F suffix C is allowable compressive stress. Lambda is what? Effective length by minimum gamma. After knowing this, come to the now problem. We know all this representation, and know this will help when solving the problem. Now come what the question is saying. This is the question. Let's see. Question is saying that determine the uniform distribution load carrying capacity of the welded plate girders shown in figure when it is used as the cantilever beam of 4 meter effective span, and check it for shear, deflection, wave buckling and wave crippling. Assume stiff bearing length as 100 millimeter. See, in figure what is given? This 200 mm BW is given, then this is 16 mm BF is given, and then this is 92 mm is given. From here to here I section beam is 92 mm, and from here to here it is total 832 mm. From I section from here to here, this is total D, and then from here to here, if you see, from here to here only, this is 800 mm, and then from here to here it is 16 mm. Here, similarly from here also 16 mm. Here to here only, this beam, this part is and then this length is also 16 mm only. This length only 16 mm, and then this is twisted. Then it is half portion is gone that side, and this is left, and half portion is left this side. So here is also 400 into 16 Fy, and then 200 into 16 Fy. Fy is what? Fy is nothing but yield stress of the wave, as I said earlier. And then 200 is here, up to here, from here to here, and similarly from here to here this 200, and this total is 800. 400, 200, 200, 600, and 200, 800. Okay, and then given data is what? Now this I have prepared earlier. Okay, so this is lengthy problem, so I prepared given data is what? Given data are effective span is equal to 4 meter. 4 meter is given here. As you can see in question is given 4 meter, effective span is 4 meter, so 4 meter, and it is denoted by L, effective is equal 4 meter, and BS is stiff bearing length is 100 meter. 100 meter is also given there in question. Stiff bearing length is 100 mm. 100 mm is also given. Now we have to find the moment of inertia about the z axis. Z axis is its formula is BDQ by 12 I section minus twice. Why we are doing twice here? Twice no need to, because it is 2 into 2b. Here see, one rectangle is up, another rectangle is down, so twice into 92 into 800 q by 12. This is for wave. Okay, and then after doing this, if you calculate in calculator, then this much value will come. You can do by yourself, and always this is in millimeter power 4. And then next we have to find the modulus of the section, and for this we have a formula. Z suffix E is equal to I suffix Z by Y maximum, and Y maximum, where Y maximum is equal to D by 2, and D is equal, D value is how much? If you see in figure, D value is 832 mm. If you see in figure, D value is 832 mm, and by substituting that value here, 832 by 2 is equal to 416 mm, and then Z suffix is equal to 1748.173 into 10 power 6 by 416, and by calculating this we will get the value 4202.339 into 10 power 3 millimeter power 3. As it is, Fy in compression at the top and the bottom, tension at the bottom, and then what happened? Plastic neutral axis is at the mid depth. Plastic at the mid depth. This is mid depth. Okay, this is I section, and this is mid depth. Okay, dot line I have taken as a mid depth. Okay, and then after doing this, we have another. We have to calculate for moment about the plastic neutral axis. For this we have a formula is equal to 200 into 16 Fy F suffix y into 816 at the top, plus also we have to do the 400 into 16 F suffix y into 400 at the bottom. After doing this, we have to substitute those value, and then finally we will get the M value, F171.2 into 10 power 3 into Fy. Okay, where Fy value is given. Okay, where Fy value is how much? Here, as you can see that there 825. By substituting that value, we can get the 5171.2 into 10 power 3 millimeter cube. Okay, after calculating this, we have to calculate for section. We have to classify this section for I section. Okay, section for I section, and for this we have a E is equal to 250 by Fy. Fy is anything but 250, and whole power I by 2. By substituting this, 1 by 1 get cancelled, and if we multiply it by 1.5, it will become 1 only. It is 1. Okay, now we have to calculate for B by Tf. T suffix F is equal to 200. B is nothing but breadth, and breadth is given 200 by 16 is equal to how much? If we calculate in calculator, then 12.5, and which is greater than 9.4, and E is less than 13.6 E. Okay, after calculating this, we have another. We have to calculate for depth also, depth for wave, and d by T suffix W, this is for wave. Okay, is equal to, and depth is given how much? 800 by 16 is equal to 50. 800 by 16 is equal to 50. 800 by 16 is equal to 50. 50, and but 50 is less than 84. So now what we can do, section is semi compact. Now we can say that now comparing both, we can say that section is semi compact, not fully compact, it is semi compact. Now adopting v sub b is less than 0.6 vd. Here now here it is comparing b is less than 0.6 vd. Then m suffix d is what? M suffix d is modulus. Okay, here, and you can see here m suffix d is nothing but it is modulus moment of the section modulus. Okay, then okay, from here we can find the beta suffix b into z into fy into 1 by gamma mo into beta, where beta is nothing but section modulus e by section modulus p. Okay, and then substituting this value, we can get the we have z suffix e by z is equal to, here z get cancelled, and then we have a formula, then we have a value 4202.339 into 10 power 3 into 250, and then where 1 by gamma mo, we have a value 250. Substituting this value, we can get m suffix d is equal to 955.077 Newton per mm. Then after calculating this, we will calculate for total moment, that is for section moment only. Okay, for wave and for flange. Okay, now we will calculate for total bending moment, and then this bending moment is equal to pc square by 2, where c square is nothing but 4. This value is given in the question. PPC in question, c is equal to given is equal to 4. C is nothing but it is span, here it is 4. Then 4. Then if we do, then 4 square is equal to 16 by 2, 16 p by, and then m is equal to 8p. 2 into 8 is equal to 16. Then taking m is equal to md, we get p value is equal to 119.385 kilonewton, and p is always in kilonewton per meter. Okay, and then now we are going to calculate for shear force, and to calculate shear force, we have another formula, V is equal to PL. Since we have P is equal to 119.385 into L is length of the span. Then substituting this value and calculating in the calculator, we can get the V is equal to 477.54 kilonewton. Okay, then after doing this, we are going to calculate for another. Okay, we are going to check now. We are going to check for shear. Okay, shear force. BD is equal to F suffix y is equal to F suffix y by root 3 into 1 by gamma mo into shear area, and shear area. Then shear area then is equal to F suffix y by root 3 into 1 by 1.1 into d into t suffix w. Substituting this value, b suffix d is equal to 250 by root 3 into 1 by 1.1 into 832 into 16. These all value is given, and we calculated earlier. Then substituting this value, BD is equal to 1746.746 kilonewton, and we have to compare this value in B with B, and since BD is greater than B, so it is less. So so it satisfy the condition, so it is safe. Now Okay, to check for deflection, we have another formula. Delta is equal to p suffix w into p l power 4 by 8 e I j I suffix z, and p suffix w is equal to working load by 1.5. This is also is equal to p by 1.5 into 100, and we by substituting p is equal to 119.38 by 1.5, we can get the p suffix w is equal to 79.587, and p suffix w is always deflection is always in Newton per mm. Now we can calculate. Since we have a p suffix w value, now we can calculate the deflection. Now span length we have, a p suffix w value we have, and I suffix z value also we have, e value also we have. Then substituting these all value, 4 value, we can get the delta. Deflection. And delta is equal to I is equal to 7.28 mm, and delta is always in mm. After calculating this, we will check for allowable deflection also. Allowable deflection is equal to effective length by 300, where effective length is 4000 by, in question it is given 4000. Okay, then from here 4000 by 300 if you do, then it will be less than that of the, if you do 4000 by 300, then how much? 4000 by 300, then it will come 13.33, which is less than delta, is equal to 13.33 mm, which is less than delta. So it is safe. Delta is greater than delta allowable, so it is safe in deflection. So it is safe. Now checking for the wave buckling. To check the wave buckling also we have another formula. F suffix cdw is equal to b1 plus n1 plus n1 into tw into fc, where b1 is equal to 100, n1 is equal to d by 2 is equal to, where d is depth, where depth is given 832 by 2 is equal to 416 mm. If we divide 832 by 2, then it will come half of that is how much? 416 mm. Then t suffix w is also given 16, and then now adapting fy f suffix y by considering the lambda value. Lambda is how much? 2.5 into d by t suffix w, and lambda is 2.5 into 816. Depth how much came? Depth is 816. By substituting this by 16, we get lambda is equal to 127.5, and for lambda 127.5, and fy is equal to 250 Newton millimeter square. We will calculate this from the table, and we can see here lambda value, lambda and fy. See, this is fy value, yield stress value in mm. This all value in yield stress value. So yield stress value, fy value is how much? Fy value is 76 is in between these 60 and 70 and in between these is how much? 127 can be in this here, 127 in between 120 and 120 and 120 and 130. So in this from code book we can calculate. So knowing the value of f suffix c is equal to yield stress value 76.65 Newton per mm square. Now we can calculate. Now we can check for the wave buckling also. And f suffix c t w is equal to b1 plus n1 into t suffix w into fc. and substituting this value 100 plus 416 into 16 into 76.65, we can get the value. We can get like this. We can get is equal to 632.822 into 10 power 3 Newton. And if we write in kilonewton, it will become how much? 632.822 kilonewton, which is greater than 477.54 kilonewton. So it is safe. Now we are going to check for wave crippling also. And wave crippling, to check for wave crippling, we have another formula. Is what? And wave crippling is always denoted by f suffix w, and its formula is b1 plus n2 into t suffix w into fy into 1 by gamma mo. So since we have n2 is equal to 2.5, tw is equal to 2.5 into 16, t suffix w is 16. So 2.5 into 16, if we do, then it becomes how much? 40. You can calculate in calculator. b1 is equal to 100. Question it is given. Then t suffix w we calculated already. It is 16 mm, and fy we have 250 from the table, 250 Newton per mm square, and then gamma mo is equal to 1.1. So substituting, since we have a b1 value, n2 value, t suffix w value, and fy value, and also gamma mo value, substituting this value 100 plus 40 into 16 into 250 into 1 by 1.1, we'll get how much? 509.09 into 10 power 3 Newton. And then after, if this is in Newton, if we have to write in kilonewton, then it will become 509.09 into kilo. In the place of power 3, we can simply write k is always 10 power 3 Newton, and which is greater than load transfer. So it is safe. So what the question is saying? Question is saying to determine the what? So question is saying to determine the uniform distribution load carrying capacity of the welded plate girder. So finally, how much we got? Uniformly distributed load carrying capacity is P is equal to 119.835 kilonewton per meter. So in this way we can calculate